This video is going to focus on some of the questions that came up in last week's workshop on ion identity networking. And if you want to apply this to your project, just open up the project in MZMine or import the data and perform feature finding and alignment and everything like you usually do. And then you end up with an aligned feature list. And in this feature list, you usually see features that have the same retention time and a very similar shape. And these features are taken from the same sample here. And these features usually correspond to the same molecule. So if we separate molecules and then we ionize in the electrospray interface, for example, we usually create sodiated and protonated and in-source fragments and so on, and they have the same retention time and the same shape. And so we group them by Pearson correlation. So if we use the cyan row here and we compare them to the orange and black intensity profile, we can see that the intensity of the cyan feature and the intensity of the different other features is well correlated. And based on this correlation, we can create a group of these features. And then to identify the ion type, we do ion identity networking on MS1 level. So we supply a modifications list. Modifications can be in-source fragments or in-source adducts and clusters. Then we add the adduct list. This is the protonated and sodiated and so on adduct. And we can also supply a number of maximum multimers. So if we ionize molecules, sometimes they are stuck together and they cluster, and then we see 2M plus sodium or 3M plus sodium and so on. And with this, we can create a network of connected nodes. So all of these nodes are features, and we have identified them as ammonium and sodium adduct, and they're just connected based on the MZ difference between these features. And they're also connected based on the feature shape correlation, because we only do this with correlated features. And then finally, they all point to the same neutral molecule. So they all point to the same neutral mass. And I've implemented this in a very modular way, because so we apply feature correlation grouping, and afterwards we create ion identity networks with only the best ion identities, only the best adducts. But this also means that some of the signals that we see are not covered in this workflow. And to create bigger networks, we can then use the another module to add more ions to existing networks. And so we supply a different modifications list and a different adducts list, and we can also look for higher number of multimers here. And then we can see that the whole network also consists of a calcium adduct and iron adduct, maybe some multimers, more in-source fragmentation, and then we can be sure that this network was created and based on very nice adducts that we commonly see, but we can also cover all the different adducts. And so if we, from the beginning, if we supply all the different modifications and we also supply all the different calcium and iron adducts, we might end up with some weird combinations of modifications and adducts. And this is the reason why we have split it into two separate modules. So you can either just run ion identity networking and stick with the best ions, stick with the most probable ions, or you can start adding more and more ions, more multimers and in-source fragments to existing networks without going into coming into problems with creating bad networks with weird adducts. And if we apply this to a real data set, we can see that I have sent this to GenePS. There's the GenePS export in MZMine, so you can directly create the quant table, you create the MGF, and also the additional edges. And the result from GenePS looks like this. So we have the different nodes, so we have the features here, And then the yellow connections here, the yellow edges are based on MS1 ion identity networking, whereas the white edges are based on MS-MS similarity from GMPS. And then we can see that we have different insult fragments, we have multimers, and we have different adducts, so sodium and ammonium and the protonated for cholic acid here. And a good thing of ion identity networking is that we bring closer together singular nodes that were unidentified before, and some of the smaller networks in GMPS come closer together to a big network. So this network consists of 3 bile acids. We have cholic acid, deoxycholic acid, and so on. And now we can see that the different protonated species are very similar to each other. So most of the protonated species are connected in GMPS, but then on the other hand, most of the sodiated adducts are not connected. And even if we take a closer look, we can see that some of these sodiated adducts, as they show a very similar fragmentation pattern to another sodiated adduct, they might be connected, and so we can bring closer together different adducts and different small networks in GMPS to the whole network. And if we apply this to a bigger data set, so we have some isolates and some fecal samples, and we only look for cholic acid analogs, we can see in the traditional feature-based molecular networking, we have multiple medium-sized networks, we have singular nodes, and the yellow nodes here are all the cholic acid analogs, and they are just scattered around in small networks and everywhere. And if we combine ion identity networking and feature-based molecular networking, we end up with a better and bigger network here, and we bring everything very close together. So all the cholic acid analogs are now in one big network, and we also reduce the number of singular nodes and the number of small networks. And in the next video, we're actually going to see how to apply this to our data set, because when we open up the batch mode, the 2 steps that you only have to take are meta-correlate and ion identity networking. So in meta-correlate, if you go on peakless methods and row grouping and meta-correlate, you can apply correlation grouping. And if you go on identification, ion identity networks, ion identity networking, you can apply ion identity networking, but this should be done with just the best adducts, because then we don't end up with weird combinations of adducts. So we should limit this to only the best adducts here. So the next video is going to focus on a very limited, very small workflow, and then the whole workflow that we're going to use for the article.